Hello everyone, thanks for coming to our presentation today. My name is Junye. I'm from the University of New South Wales. I'll be presenting our journal paper, DronePrint, Acoustic Signatures for Open Set Drone Detection and Identification with Online Data here today. So why do we need such a system? Actually, in the last couple of years, there has been a growing number of incidents where there were unauthorized drones that tried to enter limited areas such as airport or even in a British prison for one case. So therefore, here as part of a countermeasure, we're proposing DronePrint, which is an acoustic-based approach for drone detection and identification. Our proposed DronePrint system has this particular system architecture. So specifically, we take the acoustic data from a microphone, and then we apply peak normalization, and also then we extract the MFCC coefficients as our features. Finally, we'll apply the feature vector rescaling before sending them to our classifiers. Just as the training stage, there's an extra step involved. So that's the frequency warping. This allows us to augment our data set and also deal with the potential Doppler effects introduced in the sound by the drone movements. For classification, we actually have three different classifiers. So the first classifier is used for drone detection only. So once a drone has been detected, the second classifier will try to identify its manufacturer or its brand, such as a DJI or Parrot. And then finally, for each of the drone manufacturer, we also have a dedicated classifier that identifies the drone model, such as DJI Phantom or DJI Mavic. So here's an example of peak normalization on different sound frames. So specifically, we can see that different frames are normalized so that they have comparable amplitudes. This in turn will result in a reduction in the feature vector distance when we convert them into MFCC features. And so that was with a minimal noise case. So it performs really well, reducing it from 18% to 0.14%. When there's an instantaneous noise, the reduction is less compared to the minimal noise case, but still it's rough. We are able to achieve roughly 50% reduction rate. So here are just some examples of feature matrices of different sound types. As we can see clearly on the left, drone sounds by themselves are very distinctive from other sound types. So in terms of classification, we have LSTM-based classifier. So then we have a 10 time-step LSTM of 2 layers, and at the end of it, so we use a fully connected layer and a softmax for prediction. So then in terms of datasets, so we have 3 different datasets. So the first one, the dataset 1, that contains non-drone sounds. So that's used for training and testing for drone detection, manufacturer identification, as well as model identification. So that corresponds to classifier X, Y, Z. So and the second dataset is a non-background sound. So that was used for training and validation of drone detection. And a third dataset that contains complete unknown sounds. That's for testing only, and that's for drone detection. Here's just an overview of the dataset here. In terms of results, so for detection, so we have 2 different scenarios. One is a non-classes. That means the classes are being used in the training process. So as we can see here, DronePrint, that and others, they offer very good performance in terms of detection, averaging 0.95 or so. But the advantage of DronePrint really shows when dealing with unknown classes, where DronePrint is able to maintain on average 0.85 detection accuracy compared with like 0.6 or 0.7 on average for other comparable works. As for drone identification, so once again, so we have a classifier that tries to identify the drone manufacturer or drone brand. So we can, in this case, we have like Autel or DJI. And we have a third classifier that for each of the drone brands, we try to identify the exact drone models. So I think it's fair to conclude that both identification classifiers are really good, offering on average at least 0.9 in terms of accuracy. We have also evaluated the robustness aspect of a DronePrint system. Specifically, we have tested the hardware modification, Doppler effect of noise, and also increased number of classes. And lastly, we also evaluated DronePrint with real-world sound samples for detection purposes. So in short, DronePrint is able to deal with all of them fairly well with minimal to no impact in terms of detection and identification performance, details of which could be found in our journal paper. All right, that's the end of the presentation, and thank you very much.